which proton would be eliminated if the following molecule were to undergo an E2 reaction with a small base such as sodium hydroxide or sodium methoxide. So we've underlined kind of the important things we need to look at in this question. So in general, an E2 reaction, that's our concerted elimination. Most of our elimination reactions are going to follow this pathway. So in an E2 reaction, I'm just going to use X for a leaving group. Right, so in this portion where we're looking at alkyl halides, our leaving group would be, say, a chloride, a bromide, an iodide, and we will see some other good leaving groups later on. So that's our leaving group. So what happens in an E2 elimination? So the carbon that the leaving group is attached to, we call that the alpha carbon. And the carbon that is adjacent to that, we call that the beta carbon. So what happens in an E2 reaction is you have a base. So I'm just going to say, just in general, B minus to represent any base. So in this case, it would be hydroxide or methoxide. And so that base is going to abstract a hydrogen from the beta carbon. The electrons between the carbon and the hydrogen fall in to form an alkene, and that pushes off the leaving group. And since this takes place all in one step, it requires a really precise alignment of that beta hydrogen and the leaving group. So specifically, your leaving group and your beta hydrogen have to be 180 degrees apart from each other. So let's apply this to the problem that we're being asked about. So we're being told that we have a small base. So a small base, the significance of that is that a small base would favor forming the more substituted alkene, if it's possible. Right? And the if portion depends on this constraint of 180 degrees. So a small base favors the formation of the more substituted alkene. And that is because the more substituted the alkene is, the more stable it is. So your more substituted alkene is your more stable alkene. So what we want to do in looking at this molecule, we've got a cyclohexane chair. So that's significant, the fact that this is a ring, because we don't have free rotation that we would if our bonds were acyclic and we could just spin around the carbon-carbon bonds. So I want to identify the alpha carbon. So I labeled it in purple here. So let me label it in purple again. So there is my alpha carbon. And then I have beta carbons on either side. So I have a beta carbon here. That's a beta carbon. And I have a beta carbon here. So I could do an elimination from either one of those. So I want to try to form the more substituted alkene. So if I take a look, here on this blue beta carbon, I've got 2 hydrogens. So if I form an alkene there, it's going to be a di-substituted alkene. If I look down to my other beta carbon, the one I've labeled it in green, if I were to form an alkene here, I have an additional methyl substituent. So it would be a tri-substituted alkene. So ideally, I want to eliminate from this carbon. So then the key is, do I have a hydrogen at that carbon that is 180 degrees away from the leaving group? So here's my leaving group. And I do, in fact, have a hydrogen that is 180 degrees away from that leaving group. So if I were to eliminate that HB, I'm going to get the most substituted alkene, and these are in the right arrangement. So I'm going to go ahead and circle that answer. And then I'm just going to quickly draw the mechanism and the product if you're interested in seeing that. So I'm going to use hydroxide. The product would be the same with methoxide. I just had to pick one to draw. And so if this reacts with that hydrogen, the electrons from the carbon-hydrogen bond are going to swing in to form the alkene and kick off the leaving group. And so if we are to draw that, and I'm just going to flatten it out into the cyclohexane, or a flat cyclohexane structure, the methyl group is the only substituent that I have now that I've lost the bromine. And I know that the alkene is forming between the carbon with the methyl and the adjacent carbon. So I will put it in there.